on those. And then Malcolm Kendrick has put a whole book out there called The Clot Thickens, arguing for clotting tissue. He's written this paper here, arguing that atherosclerosis and end stages of that, heart attacks and strokes, are clotting tissue. Clotting is forming. So why does the body initiate clots? Well, if you cut your skin, it wants to stop the bleeding, so clotting tissue forms a scab, right? Same kind of thing can happen in the artery. If there's damage, the body wants to stop, the potential artery from rupturing, and it initiates clotting tissue. So in 1856, a guy named Rudolf Virchow claimed, and based on his research, that the things that cause clotting, which are endothelial damage to the lining of the artery, when elements of blood clump together, or when we get stagnant, interrupted blood flow. And that's still held pretty generally accepted in medicine today. These are the things that can induce a clotting response. So here's a bunch of boxes of things that have been shown to damage the lining of the artery or interfere with healing of the lining of the artery once that damage has happened. So if without insulin signaling, we don't get the signal for growth and repair, and that interferes with the ability of the lining of the artery to repair itself. But there's many things on this list. Things we talk about a lot here, the fluctuating blood sugars, glucose-based metabolism can all increase inflammation. Endotoxemia was mentioned. Toxin exposure has been mentioned. Lots of different things. Erythrocyte sedimentation rate is a measurement of how likely or how readily your blood cells clump together, red blood cells. And it's been shown to be a very good marker of heart attack, stroke, heart failure, and atherosclerosis. And blood flow, or poor blood flow, stagnant blood flow, or in the case of arrhythmias, interrupted blood flow, has also been shown to be an indicator of clotting risk or likelihood to clot. They call it residence time of blood in an area. So it's the difference between, a flowing river and a stagnant puddle. I would argue that this world doesn't tell us much about clotting. It can tell us lots of things about metabolism. It can tell us, if there's some inflammation, if we get more damaged particles. But yeah, it doesn't tell us much about clotting. So we cannot solve our problems with the same level of thinking that created them. So we all know the story of Ancel Keys and how he created this problem, that cholesterol was the problem. And I think that analyzing lipids are not going to give us the solution to what actually causes heart disease. So we need a new level of thinking, and I would say that that's water. We're all told that we are a large percentage water, and it turns out that water has some very unique properties. And so water, what's called exclusion zone water or structured water or bound water, there's lots of different names for it in the research because lots of different researchers have come across it and kind of called it something different. But there's many research that have looked into this. The one who's made it most famous is Gerald Pollack at University of Washington. He's a bioengineer, which is interesting, an engineer coming across this. But Gilbert Lang, Albertson Georgi, Maywan Ho, James Clegg, Jim Oshman, there's many researchers that have come across this idea that water has these unique properties. So what is exclusion zone water? So when water holds energy, which it can absorb energy, radiant energy, and it gets next to a water-loving surface, it actually structures itself onto that surface. So what it does is one of the oxygen and hydrogen, one of them, they cleave off this hydrogen, and these team up with other oxygens and hydrogens and form this lattice-like structure. And when they form like that, they kind of form these planar panel things, and they kind of line up like this. And this area here, this structured water, it's structured because it's more like a gel. It's not quite ice, like solid. It's not liquid. It's more like a gel, like the consistency of a raw egg white. That's what I would describe it as. And so in Pollack's work, he found that this phenomena does happen on vascular endothelia. Structured water does form on the lining of the artery. And so it's kind of depicted here. It's formed on the outside, and those hydrogens that are cleaved off are pushed into the middle. And so here we have a depiction endothelial cell, glycocalyx, which I'm glad Dr. Diamond brought up. And then on top of that, we have this layer of structured water, which this picture is a little bit inaccurate, which we're going to see in a minute. These authors didn't understand something about structured water, but this is kind of the best picture that I found of it. And then in Malcolm Kendrick's paper, he mentions this anticoagulant gel layer on top of the glycocalyx. And so The reason that it's called exclusion zone water is because when these kind of planar things line up, they don't line up like exactly stacked on top of one another. They line up kind of offset like that. And it makes it so there's a very small space for anything to penetrate that. Dr. Pollack in his work notes that the protein albumin was excluded. It could not penetrate this exclusion zone water. It almost becomes this impenetrable barrier. And that's unique, or that's important because protein's the smallest, or albumin is the smallest protein in the blood. So if we look at the size of albumin, 3.8 nanometers, what are some things in the blood that are bigger than that? Red blood cell is way too big. It's not going to penetrate exclusion zone water if it's intact and healthy. An LDL, also way too big. HDL, too big. Sodium ion is actually also too big. And so the cutoff is sodium and potassium. So this is right here. Potassium can penetrate structured water, can get into that little space. Sodium cannot, which anybody familiar with cellular physiology hopefully is like, oh my gosh, sodium-potassium pump, right? So is it a pump or is it structured water that's creating that cellular diversion or distribution? And nitrate ion can also penetrate as well. It's small enough, which is important. Nitric oxide secreted by the endothelium. And so it's based on this Hofmeister series of size of hydrated ions. And so here it is in order, and the cutoff is here, sodium, potassium. So here it is depicted, and you can see that the inaccuracy here is that the LDLs are depicted in the middle of the structured water, which would not happen because it's exclusion zone. And so again, structured water forms on the outside, hydrogen ions in the middle. Now the other thing about structured water is that when it forms like this, because the oxygen is a bigger molecule and it's more negative and it's only got one hydrogen now, it's a very electronegatively charged area. And those hydrogen ions that line up next to it are very positively charged. And you get a positive next to a negative, that's a battery. Okay, we all have the little batteries. We put them in there. We organize the positive and negative charge a certain way. And they've actually shown in Pollack's lab that you can put an electrode in the negative area and the positive area, and you can power a light bulb. And also, this charge separation that creates energy has been shown to create flow. So they put a water-loving tube or a hydrophilic tube in water. They put it in the water and they shine radiant light on it, and the water just starts to flow with no pump acting on it whatsoever. And Dr. Pollack says that flow of this nature could persist indefinitely. Sustained water flow occurs inevitably in almost any scenario involving EZs and radiant energy. This is a video from Dr. Pollack's lab showing that structured water does indeed form on the lining of arteries, and that the blood flows after they euthanize the chick. They stop the heart from beating, the blood continued to flow, they put radiant energy on it, it continued to move. Now, the other thing is that the lining of the artery is not the only biological surface or water-loving surface. Elements of blood are also water-loving surfaces. And so structured water forms on elements of blood, like red blood cells, lipoproteins, anything in the blood, really. And because of that, we get this net negative charge around it, because structured water is very negatively charged, and they call that zeta potential. Okay? So what this does is it creates this kind of a protective area around the elements of blood, and they're attracted to the positive area around it because of the hydrogens. But if they get too close to each other, these like charges don't like each other, so they stay evenly spaced, and they don't clump together. And these are some studies that show that lipoproteins indeed do have a zeta potential, which plays an important role in lipoprotein structure and their interaction with apolipoproteins and enzymes. So the structured water is critically important. So Virchow's triad in exclusion zone water. Easy water protects the artery from damage because it excludes things that are not it. Easy water prevents hemodynamic changes by keeping blood flowing and moving. And easy water prevents hypercoagulability because it keeps things evenly spaced by maintaining zeta potential. However, there are things that can break exclusion zone water down. Remember, I told you that it's very electronegatively charged. It has a lot of negative charge to donate if something wanted that charge. And so that's what we know of as oxidative stress. Dr. Pollack calls it an electron-hungry process. And so that could be oxidative stress, inflammation. I call it low body charge, because ultimately it's all about increasing electrons into your body, and there's many ways we can do that. And when we don't have enough electrons, then it can get stolen from structured water, it can get broken down. So there's a free radical. And so when that happens, it breaks down the structured water, now leaving access to the glycocalyx and the endothelium. And it can also, when it happens in red blood cells, they can break down the structured water. Now they're clumping together because they don't have this barrier keeping them spaced. And when we're measuring particle size for LDL, when they get oxidized in small, dense particles, they've lost their zeta potential, and they're more prone to damage. Yeah. And so 2 steps, we want to do things that build exclusion zone water, and we want to avoid things that damage exclusion zone water. So these things all cause inflammation and damage the structured water. And radiant energy in the form of infrared light is the #1 thing that builds structured water. According to Dr. Pollack's lab, you can see how much it grew. And this is evolutionary consistent because 42% of the sun's rays are infrared. So things we can do to create easy water: drink good water, obviously. Avoid toxin exposure. Glyphosate has been shown to break down structured water. Avoid non-native electromagnetic fields because they reduce EZ 15 to 20%. Optimize your circadian rhythm. Eat good fats. Grounding and earthing, like putting your feet directly on the earth, has been shown to increase zeta potential and increase blood flow. Infrared light exposure has been shown to heal the lining of the artery. Exercise to the point of creating heat. Cold exposure and positive, loving relationships expressing gratitude has been shown to increase structured water. So how did I fare? My diet stayed the same. My exercise stayed about the same. My stress, unfortunately, stayed about the same, maybe even got worse. And my lipids stayed the same because I stayed on a low-carb diet. The only thing I did recommended by the hospital or the doctors in the hospital was I was on a blood thinner for 6 months. Despite the 5 medications recommended, that's all I did. I did a lot of infrared sauna. I did a lot of grounding and sunlight. Okay. And my ejection fraction improved to 50 to 55% in 3 months. And my heart tissue went from severely akinetic to mildly hypokinetic. And then a year after this, I got my ultrasound of my leg. It improved to 0 to 49% blocked to 0% blocked in 2 years. So this, I don't think, is ever going to tell us exactly what causes heart disease. And we need to change, but changes in normative science rarely come from within, which is why I'm a huge fan of places or conferences like this. So thank you.